Hello everyone, welcome to my presentation on the influence site, class and code evolution on the seismic performance of a four-story building. My name is Novel Rabani and I am a member of engineering faculty at Universitas Pekalongan. This research focuses on the seismic performance concrete four-story structure in Pekalongan, Indonesia, aiming to provide insights into optimizing structural designs for earthquake resilience in urban areas. In this video, I will guide you through the background of research, method, results, and the key implication of the study. I hope you find this presentation informative and engaging. Before I begin, I would like to express my heartfelt gratitude to the 6th Borobudur International Symposium for providing this incredible platform to share and discuss our research. This symposium plays a vital role in fostering collaboration and advancing knowledge across diverse fields, and I'm truly honored to be part of this event. Let's get started. We start at the background of the research. The safety and resilience of buildings in seismically active regions like Indonesia are critical due to significant earthquake risk. Indonesian seismic standards have evolved over time, but many existing buildings designed under older codes may not adequately withstand modern seismic limits. So we started at 2002 and then 2012, and lastly we have 2019 codes. Variation in fault class further influence building responses to earthquakes, underscoring the need for updates evaluation. Investigating how seismic code advancement impacts structural performance is essential for identifying vulnerabilities, informing retrofitting strategies, and supporting sustainable urban development. Okay, this is the differences between the 2002, 2012, and then 2019. So this is the hazard map of earthquake in Indonesia. And then this is how we design our response spectrum from 2002 to 2012 and then 2019. This is the difference between the codes. So in 2012 code, we only use the zone-based response spectrum, and the 2012 code, we use the site coefficient, and then 2018 we use the same. The difference between the 2012 and 2019 in the parameter response of the site class of the FA or FV. Okay, so based on this, how does seismic code updates affect the forces acting on the structure, and how does the structure respond to the increased demand for capacity caused by evolving seismic provision? Okay, the method we use is the finite element modeling using ETABS with the data as follows. A four-story building with concrete with the grade of concrete 30 MPa megapascals and the grade or FY we use 420 MPa. Okay. And then the load on the structure we use and the gravity load at the dead load we use on the floor at 1.49 kilonewton per meter squared, and then the roof we use 1.01 and the walls use 2.5, and then the live load we based on SNE 17 to 27 2020 with office room with lobby and the roof. And then the load on the structures based on seismic load or response spectrum, we use site classes as of SC, SD, and SE for each the codes at 2002, 2012, and then 2019 code. Here is the picture of the seismic load that we use on the structure. This is the modeling. This is the 3D model, and then this is the x-axis portal, and then this is the y-axis portal. Okay, we came into result and discussion. This is the joint reaction results. So as we can see here, at the fx of SC, SD, and SE from the AX combination give a higher than the FY from the EY combination, and respectively from the bottom, this is the moment forces. The moment forces actually the MY and from the EX actually give higher than the MX from the each of the standard. This implies from the 2002 and 2012, significant increases are observed in all parameters. Site class SC generally show larger percentage increases compared to SD and SE. SD parameters experience moderate increase from around 25 and 45. And then from 2012 until 2019, percentage increases are generally smaller, with some parameters showing minor decreases. SD shows a consistent increases across the most parameters, around 5 until 9%. SE exhibit near zero or slightly negative changes, indicating stability in seismic forces value in softer soil conditions. Okay, and this is the beam forces. This is at the midspan of the beam. As you can see here, that this is the data. And from the beam forces at the midspan beam, from the shear force or P2, the increase in the shear force over time reflects the evolution of seismic codes, particularly for SC and ST, where stricter provision led to higher demand on the beams, as is show less variation, likely due to higher initial design provision in 2002. And then the bending moment or M3. Minimal changes in M3 suggest that beam flexural demands are not significantly affected by updated seismic codes. This might indicate that the codes primarily target other structural behaviors like the shear or column design. And then this is the beam forces at the end of the span of the beam. And this is the result: significant increases in V2 from 2002 to 2012, reflecting stricter seismic requirements. From 2012 from 2019, changes are minimal, indicating stabilization in code provision. Subclass SE consistently experiences the highest V2 values, consistent with softer soil condition, amplifying seismic forces. And then the bending moment, significant reduction in M3 from 2002 to 2012, possibly to shift in design philosophy or redistribution of moments. SE and SD show substantial reduction in M3, whereas SE exhibits are more stable trend. And this is the directional influence of EX. The observed trends suggest that the seismic forces at the end of span are more sensitive to changes in V2 compared to M3. And then this is the column axial force, the data and the graphics. And then we found that the 2012 code introduced structural provision, leading to around a 5% increase in axial forces compared to 2002. The 2019 code slightly reduced axial demands in subsoils, reflecting refined analysis or material optimization. And then the axial force increased progressively from SC to SE due to soil amplification effects, with SE experiencing the highest demand. And column design for the SE require higher axial capacity, necessitating careful reinforcement and material selection. Okay, and then this is the best direction on X direction. This is the data and this is the graph. Okay, the 2012 code significantly increased base correction demands, especially for hard and medium soil sites. The 2019 codes appear to stabilize or slightly optimize base correction for subsoil, suggesting refined seismic analysis technique. Subsoil or SE continue to exhibit the highest absolute base correction, with relative increases are smaller due to already high starting value. The structural elements in SC and ST require a significant design adjustment to meet increasing base reaction demands. FE design benefit from slight reduction or stabilization under the 2019 codes, potentially optimizing the material usage. Okay, this is the SC story drift. You have three: the SC, ST, and SE story drift. This is the SC, and then this is the ST, and this is the SE. So from the data, we found that maximum study drift generally occurs around 8 meters, 8 for all soil types and load direction, aligning with expected dynamic behavior where mid-story drift is the highest. From 2002 and to 2012, significant increases in drift are observed, particularly for harder soil. This reflects the increased stringency in seismic design, leading to larger lateral forces. From the 2012 to 2019, drift stabilized for soil and show minor increases for harder soil, suggesting refinement in code provision for soft soil. Soft soil exhibit the highest drift value across all codes due to greater seismic amplification. Hard soils have the lowest drift value, reflecting smaller seismic demands. Medium soils exhibit intermediate value with increasing amplification over time. Okay, this is the conclusion. As seismic codes evolved from 2002 and 2012, there was a noticeable increase in seismic forces. which reflect the stricter safety measures in newer codes. The forces continue to stay high in 2019. The actual forces on column and beam force have increased over the years, showing that the structure is required to resist larger force and newer codes. The best reaction is also increased with newer codes, particularly for building on soft soil, which experience more seismic amplification. Structure on hard soil have lower seismic forces and drift, meaning they need less reinforcement on building. Medium soils experience moderate seismic forces and drift. The structures need a balanced design to manage lateral forces. Structures on soft soil face the highest seismic force drift, making them more vulnerable. This building requires stronger design to resist axial forces. Storage drift has increased over time, especially with medium and soft soil. This means buildings are expected to move more during an earthquake under newer codes. Soft soil buildings show the highest drift, requiring more attention to lateral resistance to prevent structural damage. Drift remain low for buildings on hard soil, even with stricter codes, but still need to be controlled. Newer seismic codes make building more resilient, reducing the risk of damage during earthquakes and the need for expensive repairs. Modern codes help create more sustainable building by optimizing materials use and minimizing the need for post-earthquake reconstruction. And this is the conclusion of my research. Thank you for listening and see you again next time. Bye bye.